Okay, we're off to we're gonna go chapter 14 next, why not? And we're gonna do 14, I think 15, then we'll curve back to 11, I think, after that, and fit that in there. So this is gonna start exam 4 material. So this will be exam 4 material here. So this chapter is not too long. We're talking about liquids and solids. We're gonna talk about water. We're gonna talk about sort of phase changes, and we're going to talk mainly about intra and intermolecular forces in this particular chapter. So let's get started with water and its different sort of phases and some of the properties that we see with water. Um, Water obviously is colorless, tasteless substance. One of the things you should know is that the normal freezing point, melting point there of water is 0 degrees Celsius. The normal boiling point of water is 100 degrees Celsius. Remember, as we've talked about, I think previously, when we do those sort of transitions going from solid, say, to liquid or liquid back to solid, which is obviously melting and freezing, they do happen at the same temperature. And that is the normal sort of freezing point for a substance. It's a normal boiling point. That's where we see the transition of liquid to gas and gas back to liquid. Obviously, evaporation and condensation happening there. So, vaporization and condensation again also happens at the same temperature. Uh, it's really, again, not until you get a little bit above 0 degrees that you really sort of transition fully into the next state at like exactly 0 degrees. In the case of water, you have like ice crystals present. So you got a little bit of both phases happening at once. Same thing there at the boiling point. At 100 degrees Celsius, you got a little bit of liquid and you got some steam sort of happening, not until you get above or below that you again sort of fully transition into the next sort of phase. Water does expand as it freezes. And one of the unusual sort of properties of water is water in its solid state actually is less dense than water in its liquid state. And that's unusual for a lot of substances. A lot of substances is the opposite. In their solid state, they are more dense than in their liquid state. As we'll see a little bit later on here, the density of water in its liquid state is about 1 gram per milliliter. And that's usually the density volume that you use for water if you ever need it in a calculation. It does change with temperature. So technically speaking, temperature is really not 25 degrees. Then we usually don't use 1 gram per milliliter, but I would say probably 99% of the time, that is probably the density value that you would use for liquid water. Ice, on the other hand, as you can see, is 0.917, which is less dense than liquid water. And that is because when water molecules come together, for example, in ice, as we will also talk about in this chapter a little bit more, they are basically attracted to the positive side of one molecule and the negative side of the other. And since water is a polar molecule, the oxygen is more negative than the hydrogen. So they do what we like to call hydrogen bonding here between different water molecules. And what ends up happening is when we get a lot of water molecules sort of coming in and bonding, it will create this really kind of open sort of section between the different water molecules, especially in the ice state. Obviously, as it's going into the solid state, it's losing energy to do so. So they're not moving around as much. So they actually, because of this hydrogen bonding, which is a pretty strong sort of attractive force, it actually kind of keeps their distance from each other. So they're able to kind of keep a pretty good distance in the case of ice. And that affects the density because if you think about the density equation that we've talked about previously, which is mass over volume, what that essentially does, because there's all this open space between the water molecules, it kind of bloats the ice and it gives it a much larger volume. So you end up with like a larger number on the bottom there divided by a smaller number on top, and you actually end up with a lower density for ice than you do with liquid water. In the liquid state, even though there's still sort of hydrogen bonding happening, they have enough energy to frankly get a little bit closer to one another since they still have enough energy in that liquid state. and they're able to really kind of still get in there a lot closer than they can when they enter, as opposed to when they enter in the solid state where they have a lot less energy. They're not able to really kind of push themselves in as close to one another. And again, that's a very unusual sort of property of a substance. We again typically do see things being more dense in their solid state than their liquid state. Any questions on that there? That's a heating cooling curve. We'll talk about that in just a second. We'll come back to it. Now, when we're talking about changing states and really going from one state of matter to the next, there is a certain amount of energy that's required to do pretty much nothing more than just that, just nothing more than just taking the substance from, say, solid to liquid, or going from liquid back to solid. Has nothing to do with changing the temperature. So as we talked about, that occurs at the same temperature. So it will have nothing to do with sort of moving the temperature around or anything like that, but it is just the energy simply just to change the state of things. As we go from solid to liquid, or liquid back to solid, the amount of energy required to do that is what is sometimes referred to as the molar heat of fusion. That's also sometimes abbreviated with that delta H, which is that enthalpy symbol that we saw earlier on when we talked about energy in chapter 9, I think it was. And it's sometimes referred to as the delta H of fusion, which is 6.02 kilojoules per mole. That is roughly, if you kind of do the conversion, roughly about 335 joules per gram, required to do nothing more than, again, take a substance from solid to liquid, not changing the temperature. This number here is specific for water. And if you are not dealing with water, you would have a different heat of fusion sort of value. Remember that as we go from solid to liquid, that is an endothermic process, which means it would be positive like 335 joules per gram to basically change water from ice to liquid water. And as we go from liquid to solid, it's an exothermic process, which means the number's the same, just the sign is different. It would be minus 335 joules per gram. So as we did talk about in that energy chapter, remember that if we have something that is endothermic, that is heat and energy is absorbed. And usually the energy value is a positive number. So when we see a positive number for energy, that implies a endothermic type process. And that's different than an exothermic process, where heat and energy is released. And those values typically are negative. So it does require the same amount of energy, regardless really of which way you're going. The only difference is going to be the sign of that energy as you go through there. So this would occur in the case of water at 0 degrees Celsius is where we would have this occur. Now for water at 100 degrees Celsius, that's the normal boiling point of water. And that's where we do get our transition of liquid to gas or gas back to liquid. And to do that transition, that is what is known as the delta H of vaporization. And for water, it's about 40.6 kilojoules per mole, or roughly 2260 joules per gram to do so. And that is also the same sort of sign relationship here. As we go from liquid to gas, it's going to be an endothermic process. So you would have to put in there 2260 joules per gram of a substance of water. And if you're going from gas to liquid, you would have to remove or release 2260 joules going in the opposite direction. We can see here also from these two numbers, it takes more energy to do solid to liquid or liquid to gas. It takes a lot more energy to do the liquid to gas transition, right? About 2260 versus 333, about 7 times less, right? And that is because as we go from solid to liquid, everybody's still relatively close to one another. But as we do that transition from liquid to gas, you got to completely break everybody apart from one another to get them into the gas phase. So it usually requires a lot more energy to do that transition. Any questions on that there? So if we look at this sort of heating cooling curve, we skipped over there right here. This is a heating cooling curve, heating going from solid, which is ice, to liquid in this area, to steam, which is gas. So obvious heating going from solid to liquid to gas. It is a cooling curve if you're starting at gas and going the opposite direction, going from gas to liquid to solid. It is going to be a cooling curve. So where we're talking about right here, for example, for water at 0 degrees Celsius, we can see that the line has plateaued. And because it's plateaued, we are not changing the temperature, but we are changing the phase. So when you hit 0 degrees Celsius for water, you want to do that transition. Again, that is where our heat of fusion would come into play. Doing that transition of going again from solid to liquid, or the other way, liquid to solid. Up here at 100 degrees Celsius for water, we also see a flat line here, a plateau line, and that is our transition point of going from liquid to gas or gas back to liquid. That is where your delta H of vaporization would come into play. And those would be the numbers that we saw on the previous slide. And a reminder as well that those are specific for waters. So again, if you are not using water, it will have different values for the heat of fusion and different values for the heat of vaporization. And it may also have different boiling points and melting points as well, or freezing points. So they'll have some different temperatures that occur. So that's what we would use to do the transitions between these different sort of phases. But what about the rest of our curve here? So if we take a look in these other areas of the curve, say down here, all through this little blue line that I'm just covering over, that's pretty much solid all the way through that. And we're changing the temperature. So the phase stays the same, but the temperature changes starting right about here, all the way up through here. That also is the same phase all the way through. That is all liquid all the way through that little line. Temperature is changing, but once again, the phase is staying the same. And after we do the transition over here, we are all gas at this point. Once again, we are keeping the same phase, but changing temperature. To figure out how much energy is required to do that is something we already did in chapter 10. That is our good friend specific heat. Q is equal to ms delta T. And that is what we use when we are changing the temperature, but the phase of the substance stays the same all the way through. Reminder that Q is heat or energy and has units of joules or calories. M is mass, which has units of grams. S is our specific heat capacity. And remember that this is the guy with the 3 units, joules per gram per degree Celsius, are calories per gram per degree Celsius. Also, a number that you should know is the specific heat of liquid water. That is that 4.184 number that we used a bunch back then when we were doing that. That also, a reminder, is the conversion factor to go between joules and calories, right? So there's 4.184 joules in a calorie. So that's also the conversion factor to do that. And our delta T here is the change in temperature. And as we talked about when we did it, is always really important to always do the final minus the initial. And this is one of the few things in chemistry that we actually do leave the temperature in degrees Celsius, because the specific heat capacity is typically given to us in degrees Celsius. The reason, again, it's important, as we talked about, to do final minus initial in terms of the temperature is the mass is going to be a positive number, the specific heat capacity is going to be a positive number. So it really is the change in temperature, which is the only thing that could give you a negative value if you were supposed to have a negative value. So again, you just don't want to take the difference. You want to make sure that you always do that. So anywhere on this graph, if you were to sort of draw this graph or following along on this graph, anywhere where we keep the temperature starts to change, but the phase stays the same, we use our specific heat equation. Now, if we wanted to, for example, know how much energy is required to go all the way, say, from ice all the way up to steam, we basically would just do separate calculations for each of the steps and then add up all the energy values together. And that will give us our total energy to do that transition. Any questions on that there? So let's take a look at a problem where we could do that here together. So let's say we wanted to figure out how much energy is required to change 75 grams of ice at minus 3.5 degrees Celsius to steam at 102 degrees Celsius. So sometimes if you have a problem like this where you're kind of doing multiple steps, actually this graph is kind of a nice one to use to sort of follow along, each of the steps to get you to where you need to go. So for example, if we were going to start this one, we're going to start right about here. And the first thing that we would do is actually take it from minus 3.5 degrees Celsius to 0 degrees Celsius ice. So we're not going to change the state or anything like that. So let's take a look at what that calculation would look like. The very first step of our process would be to take our ice at minus 3.5 degrees Celsius ice to 0 degrees Celsius ice. So that is going to be ice all the way through, which means the state of it is the same all the way through. It stays solid all the way through. So we would use our specific heat equation in this case. Our Q is equal to ms delta T. We have our mass, which is 75 grams. Our specific heat capacity here is really important as well. This is actually ice in this case. And ice actually has a different specific heat capacity than liquid water. And so does steam, which is the gas water. Not 184 number. We would want to use the one for ice, which is, I don't know, roughly 2.03 joules per gram per degree Celsius. I'll take a shot at it somewhere in that 2-ish range. And our final temperature here is going to be 0 degrees Celsius. Our initial temperature going to be minus 3.5 degrees Celsius. So for that very first step, we would go into our specific heat equation. Again, making sure to use the proper specific heat capacity for ice. Want to do our final, which is 0, minus our initial. And that's going to get us here about 532, we'll call it 0.9 joules of energy. It is a positive number that we ended up with, which makes sense since we're putting energy in to do that, to melt the ice, to take it from minus 3.5 to 0. At this point, if we look at sort of where we're at on our little graph, the next thing that's actually going to happen is a phase change. So we actually have to take the ice at 0 degrees Celsius to liquid water at 0 degrees Celsius. That again occurs at the same temperature, right about there. So that's the same temperature, but different phase. That's where our delta H of fusion is going to come into play, which is sort of the second step that we would need to do. And if we do that, 0 degrees Celsius ice to 0 degrees Celsius liquid water, our delta H of fusion, or our phase change that's happening here. So we would take our 75 grams of ice. We will times it by the heat of fusion, and I'll use the joule number here since we're doing joules. And again, it's going to be positive because it's endothermic. And that means to do that transition, it's going to require about 125. So that's the amount of energy required, again, to do nothing more than just take that thing from the solid state to the liquid state. Again, not changing the temperature. Any questions on that so far? The next thing that's going to happen in our route to steam is we're sitting about right there in our graph. We have to actually go from 0 degrees liquid water all the way up to 100 degrees liquid water. And that would be our third step. So here, that is liquid water all the way across the orange section, which means the state is the same, but the temperature change. So once again, this is where we would use our specific heat equation to do so. So the third step of this process would go from 0 degrees Celsius liquid water to 100 degrees Celsius liquid water. And that's going to be our specific heat equation. So putting it in here, we got our 75 grams. This case, though, this is actually liquid water, which means we do use our 4.184 number. Final temperature 100, initial temperature 0 degrees Celsius, going to get us here 75 times 4.184 times 100. About 31,380. So we are progressing up this sort of curve here. We're almost to our steam, but we're still at liquid water at this point at 100 degrees. So if we take a look at our sort of graph here, the next thing that needs to happen actually is we now need to go from liquid water at 100 degrees to steam at 100 degrees. So once again, we're going to do a phase change. Temperature stays the same, phase changes. This is our delta H of vaporization that we're going to use to do that transition. So that would be our fourth step here. So our delta H of vaporization, which is 2260. So we'll take our 75 grams, times it by the heat of vaporization. Once again, I'm going to use the joule number since that's what we've been using here. Grams will cancel, and we will end up with 75 times 2260, about 169,500 joules to do that transition of taking it from liquid to gas. Now, at this point, we could actually, since we talked about it a second ago, that doing the transition from solid to liquid takes less energy than doing it from liquid to gas. We could actually see that to go from solid to liquid in this example, it's about 25,000 joules of energy. To do the transition from liquid to gas, it's about 170,000 joules, which is significantly more. So again, then we can see with the numbers that it takes a lot more energy to do that transition, going from liquid to gas as we break apart everybody. Now we're really close to the end of this one here as we are at 100 degrees steam, but we do want to end up about there, we'll call it, at 102 degrees steam. So that again is going to be gas all the way through that, which means that's the specific heat equation. And that would be our final step here. I'll just do it on this page. So our fifth step is 100 degrees steam. to 102 degrees steam. And our specific heat is needed for that. Putting it in, Q will be our 75 grams. Once again, here we do want to use the specific heat capacity for steam, which is not the 4.184 number. Believe it or not, it's actually about 2 as well. It's about 2.01 joules per gram per degree Celsius, and that is the specific heat for steam, give or take a little bit. Our final temperature here, 102 minus 100. That's going to get us there. About 301.5 joules. We have now hit going through these 5 different sort of steps, 102 degrees Celsius. If we want the total energy, we basically just add up all the steps that we did. So there were 5 of them. So we would go through and add up all the heat and energy values we got for each of those steps. And if we do that in this case, we had for the very first step, 532.9. For the second step, 25,125. For the third step, 31,380. For the fourth step, 169,500. And for the very last step here, we had 301.5, which gives us something like 22,689 joules. Or if we report it in kilojoules by dividing by 1,000, and we're looking at like 227 kilojoules of energy is needed to take ice at minus 3.5 degrees Celsius all the way up to steam at 102 degrees Celsius. Any questions on any of those steps there? We do end up obviously with a positive number, which also makes sense, right? Because again, it should be an endothermic process going from solid to liquid to gas in this case. Any questions on any of those steps there? So what would be the difference if I started up here and went this way? So I started at 102 and ended at minus 5. What would be the only difference in all those calculations? Yeah, everybody would be negative. Everything else would be pretty much the same calculation. We would go through if we were going in the opposite way, going from 102 to minus 3.5. This first guy, these guys would switch, and that would get this guy a negative. This would be negative 335 instead of positive, which would give this guy a negative. These guys would switch, which would give this guy a negative. This would be negative 2260. And lastly, these guys would switch, which would give this guy a negative. We're going the opposite direction, and we would just end up basically with a negative, right? So we have that sort of conservation of energy. Since it requires the same amount of energy, regardless of which way you're going in terms of the number, the value will be the same, right? So here again, the sign is really important when we talk about energy to make sure that we know it's endothermic or exothermic that's happening. Any questions on that there? All right, let's see here. We're then going to talk a little bit about how molecules sort of interact with one another and the forces that help them interact. The first type of force we're going to talk about is an intramolecular force. Intramolecular force means basically within the molecule. So that is really the forces that hold together an individual molecule with itself. So for example, if you took one water molecule, that is covalent bonding, sharing of electrons between the hydrogen and the oxygen. That is an intramolecular force. If you have a bunch of ions in an ionic compound, they're held together by opposites attract, electrostatic attraction. An ionic compound. That is also an intramolecular force. Intramolecular forces, which are the forces that hold individual molecules together, are really stronger than any intermolecular force that we're going to talk about, which are the forces that hold two different molecules together. So, for example, if we took water, as we talked about a second ago, the negative side of one water will be attracted to the positive side of another. That's an intermolecular force. Intermolecular force is the force that holds this entire water molecule together with the other entire water molecule. And we know that intermolecular forces, for example, are much, much weaker than any intramolecular forces because they are really the first ones to break. So when we talk about intermolecular forces, those are the forces that hold one entire molecule together with another. So as I just drew there, are two water molecules. Negative side of one, positive side of the other. And that is different than, again, our intramolecular forces. And we know that with the simple example of water because we've all boiled water before. And when you boil water, for example, the very first bond that breaks is the bond between water molecules. And that allows, for example, this guy to go off in, say, the gas phase when you boil it, this guy to go off into the gas phase. Clearly, if it was the opposite way, that the intramolecular force was much weaker, when you would heat something like water, you would get alphabet soup because you would be breaking these bonds and you would be producing like hydrogen gas and oxygen gas, which clearly does not happen, right, when you boil something like water. So intramolecular forces are always much, much stronger than any intermolecular force that we're going to talk about. So things like covalent bonding, ionic bonding, always much, much stronger than the actual ones that hold a particular molecule together with another particular molecule. So how does intermolecular forces work? It's a pretty simple idea of how molecules basically interact with each other. Pretty much this is how they interact with each other. The positive side of one molecule is frankly attracted to the negative side of another. Pretty much all intermolecular forces basically work in that simple principle, positive and negative attraction to one another. Now, there are levels of how good that positive negative attraction works and how strong it can be. But ultimately, any type of intermolecular force we talk about, if you boil it down to it, that is how that interaction is happening between molecules, positive side of one versus negative side of another. As you can see here with our two water molecules. So let's talk first off about, and all these that we're going to talk about here are intermolecular forces. And again, these are the guys that's between molecule and molecule. The first type of interaction that occurs is what is referred to as a dipole-dipole interaction. And you might remember dipole from when we talked about bonding. There are certain molecules that have this arrow, which points to the more negative side of the molecule. The more positive side has a dipole moment. And what that overall means is in a polar molecule, no matter what you do to that polar molecule, there's always a separation of how they're sharing their electrons overall, which means that they will always have a side that's more positive in a polar molecule and a side that's more negative. And that is different than in a nonpolar molecule where electrons are shared equally, which means it's kind of like a neutral molecule. There is no positive side, there is no negative side. Because of the equal sharing of electrons, we don't get that separation of charge. We only really get it in polar molecules where overall there is a unequal sharing of electrons that are happening. Dipole-dipole interaction is pretty much what polar molecules will use. if they cannot hydrogen bond, and we'll talk about, what allows something the hydrogen bond in just a second. But this is really the main type of interaction that a polar molecule will use with itself or other polar molecules when they come in contact with one another. And ultimately what it is because they are polar, you have this molecule that has that separation of charge, and it'll be no problem coming across the other side there. Also has a separation of charge, and they're just going to be able to interact with each other, bind to each other through opposite attraction here of the charges. Now, dipole is a relatively strong one, and it is really what polar molecules will use. A subsection of dipole is what we see when we dissolve, say, an ionic compound. When we dissolve an ionic compound, we get ions, for example. And we get positive ions and negative ions. And as we talked about, I think before, that's essentially how things dissolve, because the negative side of water will be attracted to the positive ion and surround it. And the positive side of water will be attracted to the negative side of the ion that's there and will surround it. This is what is sometimes referred to as ion dipole interaction. And that is basically the interaction that occurs when you dissolve an ionic compound in something like water. It allows a polar molecule, which is the dipole part of the name, to interact with an ion, which is obviously the positive or negative part of it. But dipole in general is for two polar molecules. Specifically, if you have an ion involved with a polar molecule, sometimes people will refer to it as ion dipole interaction. And that, again, is what allows it to interact really well with each other. Any questions on that there?
Bonds between atoms with different electronegativities have a permanent dipole, that is, a separation of charges, because of the unequal sharing of electrons. Some molecules which contain polar bonds do not have a net dipole. For example, carbon tetrachloride has polar carbon-chloride bonds, but the polarities cancel as a result of its symmetrical structure. It is therefore a nonpolar molecule. Even though the chloroform molecule has a tetrahedral shape, one of the outer atoms is different from the others, so the molecule is not symmetrical. This means the bond dipoles do not cancel, and the molecule has an overall dipole moment. It is polar. Molecules such as sulfur dioxide have asymmetrical structures due to one or more unshared pairs of electrons on the central atom. Sulfur dioxide is an asymmetrical molecule with polar bonds, therefore it is a polar molecule. When polar molecules, such as sulfur dioxide, are close to one another, they tend to align so that the positive end of one molecule points towards the negative end of another molecule. Attractions among polar molecules are called dipole-dipole forces.
So a reminder that, as we've talked about before, and what we're talking about here, we talk about, again, polar and non-polar, is we are talking about molecular polarity, so the polarity of the entire molecule. If you remember when we talked about bonding, right, we have sort of those geometries. Remember that symmetrical geometries are the ones that you draw where you pretty much have no dots on the central atom. All the elements on the outside are the same. Then it will be non-polar, right? If you have no dots on the central atom and all the elements on the outside are not the same, like in the example they showed there where they substituted a hydrogen for one of the chlorines, it will then become a polar molecule. And typically speaking, if you have a geometry or Lewis structure that you draw and there's dots on the central atom and all the outside atoms are the same, it is going to be a polar molecule. So that is what we're talking about here. Obviously, when we talk about polar or non-polar, the molecule for the most part is sort of what we're looking at. When they do get together, regardless of sort of the situation, in the liquid state or even in the solid state, they will do their best to try to keep moving around to maximize the attractive forces between the positive side and negative side of molecules and sort of minimize areas where positive and positive guys get near each other or negative guys and negative guys get near each other. They'll keep kind of moving around and kind of until they kind of find a happy state in terms of energy to do so. So we do try to maximize this attraction, but as you can see here, no matter what you do, there is going to be areas where positives and positives will be near each other, negatives and negatives will be near each other, but they will kind of keep moving around until they find a happy medium where they have more sort of attractive forces than they do obviously repulsion type forces that occur. Now, another force is hydrogen bonding. And hydrogen bonding really is a type of dipole-dipole interaction. It's actually the strongest type of interaction that you could have. And it is when we have a hydrogen that is directly bound to nitrogen, oxygen, or fluorine. So if you look at the periodic table, NOF there, that is upper right of the periodic table. And fluorine is the most electronegative element you could have. And in order for something to have the ability to hydrogen bond, it needs to be directly bound to a nitrogen, oxygen, or fluorine. So you got to have this deal like an H to an N, an H to an O, an H to an F, which this guy being more negative, this guy being more positive in each of these cases. So just the presence of a hydrogen doesn't mean that something has the ability to hydrogen bond. If it's not attached to one of those three, it will not participate in hydrogen bonding and things of that nature. This is basically what water does. Water is able to participate in hydrogen bonding as it's negative and positive. And here to say another water, if you wanted to. Positive negative attraction sort of happening. Here our hydrogen is directly attached to our oxygen, which allows the ability in both of these guys to hydrogen bond. If we had this guy here, could he hydrogen bond? He cannot hydrogen bond, so he has no hydrogens, right? What about if I swap this guy out here? By the way, this molecule here, polar or non-polar? It is non-polar, right? Symmetrical geometry. How about this guy? It is polar, right? Because of this hydrogen, right? So this will be polar. Can it hydrogen bond? It cannot hydrogen bond because that hydrogen is directly attached to a carbon, right? So that's a non-polar bond between carbon and hydrogen. So even though it has a hydrogen, it cannot hydrogen bond, which means it would not do hydrogen bonding, but it could do a little dipole-dipole interaction, right? Because it's polar. This guy would definitely not do either of these. And what about this guy here? Can this guy do hydrogen bonding? This guy cannot do hydrogen bonding either, even though there is a ton of hydrogens there, but none of them are bounded to the right element, so it cannot do it. And by the way, this guy is also non-polar, so we'll talk about what those two use in just a second. But hydrogen bonding needs the ability to do that. It is really the force that polar molecules use when they have the ability to hydrogen bond. Yeah. So this is what we were sort of talking about with the last one where we talked about dipole-dipole. Although it may be polar and it does not have the ability to hydrogen bond, it would use dipole-dipole like our case right here in this particular case. Now, there are a lot of molecules, especially a lot of organic molecules, for example, that actually have polar parts of the molecule and non-polar parts of the molecule. So if we look at something like our friend methanol, which you might have played with the other day. Methanol actually is an organic sort of compound, and it has actually two parts to it. This part where the carbons and hydrogens is nonpolar. But what it does also have is this part here, which is a polar bond, which is that OH bond. And because it has that OH bond, can it hydrogen bond? This guy right here can actually hydrogen bond because it has the hydrogen attached to the oxygen. So that little part of it has the ability to hydrogen bond. That's also why something like methanol, if you did the experiment last week, should have been soluble in water, because when you put methanol in with water, the methanol and the water can hydrogen bond with each other and will be able to interact well with one another and mix. And that's why intermolecular forces, for example, play a big role in things like solubility. Things that use similar types of intermolecular forces will be soluble in each other because they're using the same type of interaction that they're used to using, and it works really well. So that's why those guys would be soluble in each other. Mind you, as if you take organic eventually, if you look at something like methanol, it has one carbon, but if you added like 7 more carbons to this with that one OH group, it would not be soluble at all, because all that nonpolar part gets too big, gets in the way, it doesn't allow it to interact well with water. So there is a limit to solubility, even with things like that have an OH group. Usually in like an organic compound like that, if you hit about 5 or more carbons, you will see solubility drop out to like nothing. So you need it smaller with an OH group still able to hydrogen bond. Any questions on that there? Let's take a look at this, and we'll also see what ice and I think liquid water will look like here.
Some polar molecules have unusually strong intermolecular attractions called hydrogen bonding. These attractions occur in molecules where hydrogen is bonded to fluorine, oxygen, or nitrogen. The interaction occurs between the hydrogen of one molecule and an unshared electron pair on the more electronegative element in another molecule. The orientation of hydrogen fluoride and water molecules in the liquid states of these substances is determined by hydrogen bonding. The hydrogen atom in hydrogen fluoride is attracted to the fluorine atom on another hydrogen fluoride molecule. Water with 2 hydrogen atoms and 2 unshared pairs of electrons can form 4 hydrogen bonds per molecule. In ice, hydrogen bonds.
So you can see all the big openings in ice.
Of water molecules around one another, forming 6-membered rings that leave open channels through the ice structure. In liquid water, the tetrahedral arrangement is not fixed because the molecules are able to move around, and on average, a water molecule is surrounded by 3.4 other water molecules. Hydrogen bonding forces are unusually strong attractions that occur among molecules in which hydrogen is bonded to a highly electronegative atom.
So as we saw there, also the little thing about ice, again, big kind of opening spaces in the ice. Again, that's what causes it to have a lower density than liquid water, as in liquid water, because it has more energy. As you can see, it kind of collapses on each other. They're able to get a lot tighter to each other. Sometimes referred to as London dispersion forces. These are pretty much your weakest type of force that you have. They are the forces that pretty much are what nonpolar molecules will use. So this is really the main type of intermolecular force that a nonpolar molecule and itself will actually use. Now, because the way that intermolecular forces work, which is you need the positive side of one molecule to interact with the negative side of another, nonpolar molecules are in a little bit of trouble because they are nonpolar and sharing their electrons equally, which means if you have 2 nonpolar molecules, They're pretty much neutral. There is no positive side. There is no negative side, which makes their interaction pretty difficult for it to occur. So these dispersion forces are temporary, weak type of forces, and they have to rely upon something happening. So one way that you could sort of get a nonpolar molecule to sort of interact with something is to induce a dipole, and that's sometimes referred to as induced dipole. And there is ion induced dipole, and there is dipole induced dipole. What that essentially means is, for example, if we have our nonpolar molecule here and we butt up an ion near it, because the ion has a charge, temporarily speaking, the electrons in our nonpolar molecule are now going to be attracted, say, to this positive guy. And it's going to cause this nonpolar molecule, which normally does not have a charge, to temporarily gain a charge. And now it has a way to interact with one another until that ion kind of floats away, and then it's going to kind of break apart. The electrons are going to go back, and it's not going to be able to maintain that interaction for a really long time. Same thing would happen if you rolled up a polar molecule next to a nonpolar molecule. The electrons here would be attracted, and temporarily speaking, our nonpolar molecule will gain this temporary charge, and now they have a way to interact with each other. So this is what is sometimes referred to as ion-induced dipole or dipole-induced dipole. You're basically kind of forcing this guy that normally doesn't have a charge to temporarily gain a charge so it can do its interaction. Another way that it also commonly happens is by what is sometimes referred to as polarizability. And polarizability is the ability of electrons just to, for example, end up in the same spot. Because they're flying around, it is possible, for example, that we have electrons, say, in this first nonpolar molecule that all decide, for whatever reason, to end up on the left-hand side of this molecule. And if all the electrons just kind of flew over there all at once, it would then cause in this nonpolar molecule a temporary charge that would develop. And if that guy is still next to another nonpolar molecule, the electrons in this guy will now be attracted to that temporary positive charge. And our second nonpolar molecule will now have temporary charges. And now both of these guys have a way to interact with one another. This is why they are very weak type of interactions, because in order for them to work, something has to happen to that nonpolar molecule to allow it to gain a positive side and a negative side to interact with itself or another nonpolar molecule. Question on that there. Now, even though dispersion forces are weak, there are different strengths in terms of dispersion forces. And the strength of a dispersion force depends on the molar mass. So if you had larger molar mass, you usually will have a stronger dispersion force. The reason for that is pretty simple. If you have a larger molar mass, you probably only could get that with more atoms. More atoms would have more electrons, and there's a greater probability of those electrons kind of moving one way or the other and creating these temporary type charges. It also gives those molecules with more electrons and more atoms more places to interact with other guys using dispersion forces, and that will make it a stronger one. So, as I talked about before, intermolecular forces affect things like boiling points and melting points. So, the stronger the intermolecular force, Usually it is the higher boiling point, melting point that you have. And obviously vice versa, the weaker the intermolecular force, the lower the boiling point, the lower the melting point that you would have for a particular substance. So if you were comparing, for example, two nonpolar molecules, and one was, say, CH4 and one was like C10H22, the C10H22 would have the higher boiling point and melting point because it definitely has a lot more molecules, a lot more atoms, I'm sorry, and a lot more molar mass. So we'll have a greater opportunity for electrons to sort of polarize, also greater opportunity for interactions to occur. So if you have to pick between two nonpolar molecules and you're asked a question like which one should have the higher melting point, boiling point, it is the one that has a greater molar mass is usually the correct answer to that. Any questions on that there? This is again the main force that is used for nonpolar molecules. If you think a lot of organic molecules are nonpolar, for example, things like methane, propane, butane, right? Those are all like gases, and that's because they're held together by dispersion forces, which is relatively weak. It doesn't take a lot to make those guys go into the gas phase. Forces for a little bit of time. But it will not use it as its main source of interaction. Polar molecules will either use dipole-dipole or hydrogen bonding. That's why for a short period of time, things mix, right? Like oil and vinegar salad dressing, right? You mix it up for a short period of time, it'll kind of interact well with each other, polar and non-polar parts. But over a period of time, if you just leave it there, everybody will go their separate ways. And that's because they cannot maintain that interaction over a long period of time. They'll eventually separate out from each other. So let's take a look at that.
Solid carbon dioxide, dry ice. Nonpolar molecules are arranged close to one another in a regular array where they move slightly around an average position. The distribution of electrons in a molecule can occasionally become asymmetrical, leading to the formation of a temporary separation of charges, a dipole. Partial changes on the molecule that form a temporary dipole then influence the electron clouds of nearby molecules. Although the dipoles are temporary, there is a significant attractive force between adjacent molecules as a result of the deformation of their electron clouds. These attractive forces are called London dispersion forces. London dispersion forces are the only type of intermolecular force found in nonpolar molecules.
So to sort of summarize what we talked about here in terms of intermolecular forces, on one end of the spectrum is really our strongest, which is our hydrogen bonding. And once again, that does need to be, as we talked about, a bond between hydrogen and nitrogen, oxygen, or fluorine. And it will usually have one of these bonds in it, the HN, HO, HF type bond. Next strongest and pretty strong as well is dipole-dipole interaction. And again, this is what polar molecules will use that cannot hydrogen bond. And obviously, this is what polar molecules will use that can hydrogen bond. And the weakest of our intermolecular forces is going to be our dispersion forces, which is pretty much your nonpolar molecules. So in terms of boiling points, melting points, and those type of things, on the left-hand side here, we would expect high boiling points and melting points. Anything in this region, lower boiling points, lower melting points. This is also why intermolecular forces, as I mentioned, is a main thing of how things interact with each other. This is why polar things and polar things are typically soluble in each other because they're using the same type of intermolecular force. This is also why nonpolar things and nonpolar guys are also soluble in each other because they're using the same type of interaction. And this is also why polar and nonpolar things are not typically soluble in each other because one is trying to use either hydrogen bonding or dipole-dipole, while the other is trying to use dispersion forces, which is a very, very different set of interactions. Now, you may be asking yourself, if they're all basically positive, negative attractions, why is dispersion forces really the weakest of all of them? The real reason for that is when you have a polar molecule, no matter what you do to that polar molecule, it has a dipole moment, which means it always has a positive side. It always has a negative side. It is good to go. No matter what you do to it, it will always be ready to bond and do that intermolecular bonding. That is different than when we get over here to dispersion forces and nonpolar molecules. It doesn't have a charge. It needs something to happen to get a temporary charge for it to interact. And that's why they're way weaker than, say, hydrogen bond and dipole-dipole, because with polar molecules, they're good to go. They always got that separation. You don't need anything to happen to it to allow it to get that separation. It's good to go out of the box and able to interact. Any questions on the differences there? Okay, then let's talk about some other things here. Let's talk a little bit about evaporation, condensation, and vapor pressure. As we talked about earlier, evaporation and condensation occurs at the normal boiling point of a substance. And that is as we go, obviously, from liquid to gas or gas back to liquid. It is a endothermic process going from liquid to gas, exothermic going from gas back to liquid. Really, at any surface of any liquid, you have both of these things happening. So, for example, if you had a little bit of liquid at the surface, you got some fast moving liquid molecules that have enough energy when it starts to boil to jump out into the gas phase. You also have some slow moving gas molecules going back into the liquid phase at the surface of any liquid. And when we do get this evaporation that occurs at, say, a surface of a liquid, and when we have gas molecules above the liquid, that is what is known as the vapor pressure of a liquid, is basically how much gas molecules you have over the liquid. It is also related to intermolecular forces, which means if your liquid is a strong intermolecular force, you will probably have less gas molecules escaping the liquid easier, and you will have a lower vapor pressure than if you have something that's held together by very weak intermolecular forces. It will not take a lot for those liquid guys to jump ship and head out of the liquid part into the gas phase. And those type of liquids are what are said to be volatile, which is what a lot of organic liquids are. They may be a liquid, but again, if you sneeze at them or just look at them wrong, that is enough for them basically just to escape. Like you open the lid and that's enough for them to pop out of the liquid phase into the gas phase. And they typically will have a very high vapor pressure and be volatile. And that's because they will go into the gas phase really easily. So if you have a liquid where it's very easy for these guys to just kind of jump out of the liquid part, that's going to create a lot of gas molecules above the liquid, and a lot of gas molecules above the liquid would result in a greater vapor pressure, right? Because more gas molecules, more collisions, more pressure, and obviously less gas molecules, less collisions, and less pressure. Any questions on that there? By the way, this is also why if you put a drop of liquid, say, on the bench, you have evaporation occurring, right? And you also have guys coming back. But in the case of, say, something on the bench, you'll have this evaporation, but you have air that blows away those molecules as they evaporate, which means they're no longer there to come back into your liquid. And that's why if you have like a little drop on the bench, right, eventually it will just all evaporate off pretty easily, not too much trouble. Now, if you take that liquid and you throw it into a beaker, it's going to take much longer, right, for it to evaporate because there's a lot more water underneath the surface. And as those guys go to the surface, some will get blown away, but not as much as it's spread out all over, say, the bench top. And it's kind of evaporated at all points, right? Greater surface area. If you just spill something like this, you got a lot of evaporation happening as it's pretty much spread out. Also different is if you put a lid on it, nobody's going to escape, right? So it's not going to allow it to evaporate off, which is why we do put lids on things. Speaking of putting lids on things, when we look at, say, a solution in a container like a flask, when we first put the liquid into that container, pretty much we have a high rate of evaporation, right? Because we just put it in. And as they evaporate, in this case, as we just mentioned, they really can't escape because the lid's on there. So we're going to get some coming back, right? And starting to go through evaporation and then go through condensation. And eventually what will happen is this liquid that you put into this container will reach equilibrium. And what that means is the rate of evaporation will equal the rate of condensation. And just as quick as it kind of goes out of solution, it will go back into solution. And if you really look at the level of liquid in the container before you put it in, or right after you put it in, and after it reaches equilibrium, you'll actually see a decrease usually in the volume of the liquid. And that is because a lot of that liquid guys are now up here in the gas phase above the liquid. And that would be where we would have our vapor pressure, right? All those gas molecules above the liquid that's flying around and banging around will cause our vapor pressure. So when we put a solution in a closed container, typically that's what we observe. Sometimes it's not as easy to see, but you will see usually a slight little decrease in the volume, especially if you keep it capped and you don't open it. And that's because some of that liquid that started as liquid will have evaporated and now is basically above the liquid in the gas phase and is a vapor. Any questions on that there?